all of the steel structure completed, it's time to launch on the final and most exciting phase, the hydraulics. That was me in September of last year, talking confidently about how I intended to install the hydraulics needed to power the loader. I didn't know then about the long slog that I was really in for. You see, I had assumed that because this tractor already has hydraulics powering its propulsion and accessories, that it would be easy to tap into the existing stream of hydraulic oil flow and simply divert the flow that I need to power the loader. But it turns out that I had it backwards. It turns out that hydraulics is only simple if your system has a single component, something like a log splitter. One ram, one valve, one path for the fluid. But as soon as you introduce a single additional component, there are a series of logic inflection points that all have to be fully accounted for to ensure that both components can always get the flow that they need and that neither component interferes with the needs of the other one. The more components you add, the more difficult it is to achieve the necessary balance between each of their competing needs. Now, there are many different kinds of hydraulic flow and pressure devices, so there are a million possible design options. Each available design option brings with it a set of trade-offs. So there's no single ideal way to implement a multi-component hydraulic system. There are only alternatives, and each alternative offers some benefits and some drawbacks. So needless to say, choosing the best design for your system's needs can be tricky. It's not the kind of thing that you can just Google it and do whatever Google says. Regrettably, this is true even if, like myself, you're a clever person who's had a lot of exposure to mechanical and logical systems. So adding a loader to a machine that has no existing hydraulics at all is relatively clear and simple. To power its cylinders, that machine just needs a hydraulic tank, a pump, a control valve, and some pressure relief. And most newer control valves have pressure relief built in. So you just need to install a tank, a pump, and a control valve, hook it all up to the cylinders with the appropriate lines, and voila, you have a working loader. In my case, however, I'm adding the fifth component to what is an already intricate system. And though I had given it some serious thought and tried to do thorough research, I didn't actually understand what design options would be workable for this system, nor their inherent trade-offs. So if you're curious about my journey of discovery, about the mistakes I made and what I learned about this specific situation, then keep watching. If you just want to know what worked, then skip ahead to this point in time right here. In the beginning, in reading about adding a new valve into an existing hydraulic system, I came across the idea of a control valve that implements a feature known as power beyond. Now, in general terms, a power beyond valve only diverts the fluid that it needs for its purposes and forwards the rest to the next valve down the line. So if you're going to install a power beyond valve into a system that already has a control valve, the power beyond valve has to be installed first, upstream of any existing control valves. Once you've done that, you'll now have multiple valves in your pressure stream, and you can use either one. So I bought a new loader valve, I machined a power beyond port into it, and mounted it on the right-hand fender. Now, this tractor came from the factory with steel hard lines made from steel hydraulic tubing, flared on both ends, and connected with JIC hydraulic fittings. So I created a new set of steel hard lines using the same kind of tubing and flaring and fittings, and diverted my main pressure stream from the pump up to the new control valve, and from that control valve's power beyond down into the factory travel control valve. The new loader valve was now permanently mounted on the fender, piped into the pressure stream, upstream of the factory control valve. When you detach the loader, you would simply detach the 4 hoses leading to the work ports, but the valve itself would remain in place. At this point, I thought my new loader valve was ready for use. But I needed at least a minimal function test before I could really proceed. So to simulate sending fluid to and from one of the cylinders, I connected a loopback hose. When you pull the lever, the fluid just flows out of one work port through the hose and back into the other work port. Then I refilled the hydraulic system, fired up the machine, and went for a test drive. Now, much to my satisfaction, everything seemed to work okay. I could still drive. When I pulled the levers, I could clearly hear the fluid running through the loopback hose, just like it should. The tractor speed was normal, and there were no leaks. Hooray for me. Then, as I was driving along, I remembered that I needed to confirm what would happen if I pulled the lever while I was actually driving. What I expected to happen is that the machine would slow down a little bit, since by pulling the lever, I was diverting some of the fluid away from the pressure stream leading to the travel control system. But that test did not go as planned. As I rolled along and reached over and pulled the lever, I got a big surprise. The tractor lurched really hard. I heard a loud bang, and suddenly my head and neck and my entire right side were all wet with warm, sticky oil. I looked over to my right and saw that my new hardline, the one coming out of the new valve's Power Beyond port, had just blown out of its fitting, and oil was spraying everywhere. I'll never forget that sense of panic and confusion. So I got the tractor shut off and did my best to clean up the oil mess. And I got the tractor towed back down here to the shop and started trying to make sense of what had happened. One thing was clear. My flaring process for putting the 30-degree JIC flares on the ends of the steel hardlines was inadequate. I had been using a standard flaring tool, the type that you use for plumbing copper, and it was never intended for big steel lines. And when that tool had predictably bent, I had tried to compensate by welding crude reinforcements on the side of it. That had helped some, but I had the sense that the flares that it produced may very well be marginal. And this event made it clear that I needed a better method or tool for flaring these steel lines. But at the same time, I was fairly certain that the failed joint had, at that point, already held up to normal pressure. Because during my initial test drive, I had intentionally tried to bog the engine down to try to subject the new lines to the maximum normal operating pressure. And in that pressure, they had held up just fine. So why would the line suddenly burst when I reach over and pull one of the levers? How could pulling this lever possibly put excess pressure on that hard line? So I put everything on hold while I mused about it. And over the next 2 or 3 weeks, I went through the process in my head over and over and over again, trying to get understanding. And finally, it hit me like a bolt out of the blue. Oh, either. The key word is either, not both. You see, when you pull the lever on the upstream valve, all of the incoming fluid gets diverted to the work port. If it wasn't, then there wouldn't be any pressure at that work port, because if there was any downstream channel open for that fluid to follow, the fluid is going to follow that path of least resistance, and that's not going to leave any pressure out the work port. So the only way that you can get the pressure and the flow you need out the work port is for all of the downstream ports to be temporarily blocked off. So if you have a Power Beyond valve in line with another downstream control valve, you can use either valve, but not both at the same time. Okay, so that explains kind of what happened, in that I was starving the main travel system of fluid when I pulled that lever. But how did starving the travel system of fluid cause an increase in pressure in the line feeding the travel system? Well, you may remember from my previous videos how an electric motor and an electric generator are kind of the same thing. If you feed electricity to a motor, you get rotation. But if you feed rotation to a motor, you get electricity. Well, it turns out that a hydraulic motor and hydraulic pump are kind of the same way. If you feed fluid to a hydraulic motor, you get rotation. But if you feed rotation to a hydraulic motor, you get fluid. So here I was driving along with this spinning hydraulic motor, and I pull that lever and I cut off all the fluid flow into the motor. The inertia of the machine keeps the rotation going into the motor, and that produces pressure, and that pressure has no place to go. So it increased the pressure in that line, and the line blew. Something had to give, and the poorly done flare fitting turned out to be the weakest link. But the real problem wasn't the poorly done flare fitting. The real problem was the system design. The way I had set it up, if you ever pull that lever while you're traveling, then either the rear wheels have to lock solid, or some kind of hydraulic line or component has to blow out to release the excess pressure. Now, obviously, that's not a workable design. So it was back to the drawing board. But the holidays were here, and it was time to step away from this project for a while. And after the holidays, I had other projects that were overdue for attention. And honestly, I didn't have much motivation to return to the scene of my failure. But thanks to YouTube, thanks to you guys, I had the whole world looking over my shoulder. So I simply had to get back to this project sooner or later. So doing some further research and getting some good advice in online forums, I found that I had two general approaches available to me at this point. Either I could install a priority flow divider upstream of the factory travel control valve, or I could modify the factory travel control valve and insert power beyond capabilities into it, and then mount the new loader valve downstream of the factory valve. So let's talk about the priority flow divider first. When you're using a priority flow divider, you pipe it in place just like you would a T, upstream of both components that need flow. And just like a T, the fluid flows out of both of the ports and feeds each of the downstream systems. In our case, we'll have the loader valve and the loader components on one side, and we'll have all the factory hydraulic components on the other. But unlike a T, a proportional flow divider actually contains a control valve that operates hundreds of times per second, and that valve enforces a specific volume of fluid to the priority port and then sends anything that's left over to the secondary port. That allows it to have a key capability that at first thought seems impossible. The two different ports can operate at two different pressures. Because the flow divider can stop or start flow to the priority port, it can force the flow into that port no matter what pressure it's operating at. This device is not subject to the path of least resistance. It will always feed a chosen set of volume to the priority port. Now, in my case, that differential pressure capability can be important because the factory travel system operates at about 2,000 psi. But according to my calculations, my loader may need up to 2,500 psi if it's going to have the 1,000-pound breakout capacity at the tip of the bucket. And at this point, the flow divider seemed to be the easiest option to install because I thought I could make use of most of the changes in piping that I had already put onto the machine. So I went ahead and ordered one. But a priority flow divider is not without its drawbacks. You see, the system only has so much flow to go around. This system has an 11 gallon per minute pump, and about 2 gallons is diverted to the power steering system. That leaves 9 gallons to take care of the needs of all the rest of the tractor. When we put in a priority flow divider, we're going to be trying to balance the travel system needs of the tractor against the needs of the loader. Now in this case, if I reduce flow to the travel system, what it's going to represent is slower operating speed. And surely I can find a balance point that the machine still moves fast enough and still has enough flow to divert to the loader to make the loader useful. I think. But the only way to really know for sure is to install it and try it. But clearly, using a flow divider means that there will be an ongoing struggle to balance the flow needs of the loader against the flow needs of the rest of the tractor.
Now, when the flow divider arrived, I found that it was a lot bigger than it looked in the picture.
And if I was going to leave the new piping in place, I was going to have to mount it in place of the loader valve and put the loader valve up on top of it. And the loader valve was now going to be sticking way up in the air, and it was going to be ungainly, and it was going to make it more difficult to get onto and off of the tractor. And I wasn't happy about that. But I went ahead and at least temporarily piped it in place so I could take the tractor out for a drive and give it a test. And I found that there was actually an adjustment point where the tractor still maintained an acceptable speed, and I could hear at least some of the fluid being diverted through the loopback hose in the new loader valve. And I could pull the lever while driving without any problems. So, problem solved. Now I can move on again. Hooray for me. However, when I really got into it, no matter how much I played with the physical layout of these two new valves, turning them sideways, putting one in front, the other behind, putting the loader valve up high, putting the loader valve in front, I couldn't find a configuration that I felt like was actually acceptable. I felt like I'd made it this far in this project, doing things to a pretty good standard of usability and appearance, and now I was gonna blow it by having this big, ugly stack of hydraulic components sitting there on the right-hand fender. So I decided I just had to find a different place to put the flow divider. And that search led to two more aha moments. Firstly, in looking around, I had decided that I could shoehorn the flow divider down here underneath the driver's seat behind this panel where I currently have the selector valve, and just leave its control knob sticking out the top. But to do that, I was going to have to remove and completely move and reinstall the selector valve that I had just done all this work to get installed. Then I was going to have to create new hard lines from the pump to the divider and new lines from the divider out to the rest of the tractor, including the loader. And then inspiration struck. If I'm going to have to reroute all these lines anyway, what if I moved both the flow divider and the new loader valve? It hit me for the first time that I actually could mount the loader valve up here on the frame of the loader itself. And that way, the valve detaches with the loader. And instead of disconnecting 4 lines from the work ports every time you remove the loader, you only have to disconnect 2 lines. The line feeding the valve and the line returning from the valve. That's a better deal all around. The valve is less intrusive when it is installed on the machine, and it completely disappears when the loader is removed. And the removal process is actually simpler because we only have 2 quick disconnects to work on instead of 4. I don't know why it took so long for this option to occur to me, but I was very pleased with the idea when it hit me. So I crawled down under the tractor to begin the work of tearing out the new hard lines and starting over. And then I had to face an unpleasant fact. Shoehorning this big old divider valve into the very confined space there was going to be just shy of impossible. There's just barely enough room to cram the big component in there and still fit the selector valve and the other things that have to be in there, and then 3 big hard lines have to be connected all up to it. So I'm going to have to move the selector valve. I'm going to have to reroute all the selector valve. I'm even going to have to reroute some of the factory hard lines to make room for it. And those steel hard lines are really stubborn. They're really frustrating to work with, especially when you know you're working with substandard tools. And so I realized that I was in for a really hard fight. Such a hard fight, in fact, that it made me reconsider option B. Remember, a flow divider isn't the only workable option we have. Our other option was one that I initially had dismissed, mostly because it meant so much work, but also because it includes a large element of the unknown. I wasn't certain if it ever had been done or if it even really could be done. And if it was possible, I wasn't at all sure how to go about it. But if the process of installing a flow divider is going to end up being overly onerous anyway, then I might as well at least consider the other option, which is modifying my stock travel control valve and machine a power beyond port into it, and then feed the new loader valve from that power beyond port. Recall that this whole project was inspired by a mini loader manufactured by the Case Tractor Company. And those mini loaders utilized that exact power beyond scheme. So if I could install the travel control valve from one of those original Case loaders, then I could just use its power beyond and direct it to my loader valve. But that's not an option. I've only ever seen one or two of them for sale, and they sold for upwards of $500 each. However, my existing travel control valve was manufactured in the same plant by the same company. And it does have a boss cast right into the steel body of the valve that's the proper location for a power beyond port. And it's even marked PB. So if I could machine a power beyond port into my current travel valve, then it ought to be functionally equivalent to the factory-made version, I think. But my travel valve is decades newer. The design has evolved a little bit through the years, so there's really no guarantee that it'll work. And I may damage or destroy my existing valve. I don't even know the precise dimensions or shape of the factory power beyond port. I'll have to basically design my own as I go along. So while it would be great to add power beyond functionality to my current travel valve, I wasn't at all certain that it was possible. And before I could consider doing anything to it, I had to get it out of the tractor. And that's no small feat either. It's hanging upside down in this dark, cramped space between the frame rails. And you have to remove a veritable rat's nest of hydraulic hard lines and mechanical control linkage and the tractor wiring and the mounting bolts, and putting it all back together is even worse. So if I tried this route, if I did all this work and it failed, I would be wasting many hours, work and effort and frustration, and potentially cost myself hundreds of dollars of replacement parts, all for nothing. So there is some real risk inherent to this approach. On the other hand, there are also some meaningful benefits. The first benefit is the knowledge, if I can do it, it will definitely work in the real world. Case built many loaders using this exact approach, and most of them are still in use today. And since the pressure stream isn't being divided, there is plenty of flow to go around. The travel system gets its flow first, so it will never be starved of fluid. And I know that the original Case loaders could operate both the travel system and the loader functions at the same time. So mine should behave the same way. And there are fewer overall components to install, fewer hydraulic lines to be run, and that should result in a tidier, more professional looking final product. So how do I choose? I realized at that point that both approaches represented about the same cost, whether measured in dollars or hours or difficulty. The flow divider approach offers higher pressure to the loader, but lower flow, which means the loader will be slower and less responsive all the time. And I'll have this ongoing struggle to balance the flow between the loader and the travel system. Whereas if I try to add power beyond to my current travel valve, it is a tried and true method. It will be neater, it'll be cleaner, and I think it'll result in a speedier, more responsive loader. But the loader bucket itself may end up being weaker than I had hoped for. And I may get way down that road only to find out that it can't actually be done, and then be forced to undo all those efforts and potentially spend hundreds of dollars in parts, only to get back to square one. Now, for some time, I had been discussing it with other Case and Ingersoll enthusiasts, and from there, one person told me that he knew for a fact that it's possible because he personally had done it. Another actually had an old Case loader valve on hand, and he disassembled it and shared photos and detailed sketches of the Power Beyond features on that valve. So armed with this information, I ultimately decided I might as well just do it the right way. And that means machining a Power Beyond port. So, as I went to remove the factory travel control valve, I was struck by just how close it is to the tractor's frame rail. Now normally, you screw a Power Beyond sleeve about this big into the side of a control valve, and then the Power Beyond fluid comes out the side of there. That sleeve slides in right at the point that the internal pressure galley is dumping into the return to tank cavity. The Power Beyond sleeve captures the high pressure fluid from the galley and prevents it from dumping to tank and sends it instead outside the body of the valve. From there, it's connected to the next component down the line. Sticking out of the Power Beyond port, we'll need a sleeve that's at least about 1 inch tall, and then we'll need 1.5 inch long swivel coming out of there. But in this case, we cannot physically fit those components. There's only 1.5 inches of space between the edge of the valve and the solid frame rail. So either I have to scoot the valve over and repipe all the lines leading to the valve and all the mechanical linkage to it, or I have to get creative and create a single fitting, a combination Power Beyond sleeve integrated into a swivel. So I decided to just try creating that special fitting. Working from the detailed sketches of the factory Case Power Beyond sleeve, I drew up the modifications necessary to machine the Power Beyond into the swivel side of a standard number 10 SAE swivel. We'll be creating the actual sleeve part and then boring out the swivel fitting to receive that part we create. Then we'll silver solder it in place and join those two parts as one. I removed and completely disassembled the travel control valve. I took lots of pictures, made careful notes of what went where. I cleaned out the existing hole that leads to the boss marked PB and examined the interior of it just to confirm that the internal cavities matched up with the sketches and photos that I'm working from. There were no big surprises. It looked inside the way I expected it to look. When I'm done with the valve, it'll have a perfectly smooth inner bore down inside the pressure galley, and our sleeve will have an external O-ring groove that will seal against that bore. So when we slide the sleeve in, that O-ring will seal between the pressure galley and the new sleeve. So that internal bore has to be perfectly round and smooth, and we'll be using a standard boring head to accomplish that. Meanwhile, the outer wall of the valve will be threaded and will be chamfered so that a number 10 SAE fitting can screw in there and the O-ring will seal against the bevel. Our threads have to be clean and strong enough to hold that fitting firmly against the 3,000 psi pressure trying to pop it out of there. And our face and chamfer have to be perfectly smooth so that that O-ring can seal against it. So I'm going to need two different specialty tools. I'm going to need a 7/8-14 tap to create those threads, and I'm going to need a reamer to prep the hole for the tap and create that smooth outer face and chamfer. I'll be making both these tools because if they are available for purchase, they're going to be outrageously expensive. For the tap, I used an old trick that I found on the web. To create any tap, you can just machine the male threads that you want onto some high carbon steel, then heat treat the steel, and then grind 4 bevels that effectively put a taper onto the leading edge of the threaded portion. Each of the corners of those bevels becomes a cutting edge to carve out the thread channels. I've used this method before, and though it's not as crisp and smooth as a factory-made tap, it's very predictable in that you can't really do much to mess it up. It only works okay, but it's consistently okay. They don't break off, they don't have any other ugly surprises. So I cut a 7/8-14 threads onto some water hardening steel rod and hardened and tempered it, and then ground back the 4 leading bevels. For the reamer, I used the same water hardening steel rod. I turned it to the diameter and profile I needed, and after heat treating it, I cut longitudinal slices into it to act as the cutting facets. I tested both these tools on some spare cast iron just to get a feel for how well they'll work before I cut into my precious valve body. I ended up making some refinements to the reamer because its channels were too narrow and were filling up with swarf. I widened up those channels a bit and tried it again, and the second test went fine. So it was time to mount the valve into the mill vise. I got it carefully squared up and centered on the internal pressure galley. First we'll create the inner bore in the pressure galley, so I drilled to a size about 100 thousandths under the final diameter I was looking for, and then used the boring head to open it up to its final finished size, using a snap gauge as I went along to measure my progress. With the inner hole complete, I drilled the outer wall big enough to use the reamer, then ran the reamer in using plenty of lubricant and very slow spindle speed. Finally, I ran the tap down into the reamed hole, again with plenty of lubricant. So now the machining was complete. I cleaned out the valve body, washed out any grit and swarf with compressed air and multiple baths of solvent, and then I reassembled and applied a final coat of paint. Now there's no easy way to pressure test this without reinstalling it, so I guess that's what we're doing next. While I was doing all the work to remove and reinstall the travel control valve, I went ahead and fabricated a new set of mechanical linkage from the travel lever to the valve. The linkage is a common wear item, and using ball bearings holds up better than the factory ball swivel joint design. It's also time to make the final decision regarding the paths for the hydraulic pressure and return flows. Now, because we're redirecting the main pressure feed line, we're essentially redesigning the entire system. In the old design, there are 3 lines connected to the travel control valve. The high pressure feed line coming from the pump, the big low pressure return to tank line heading up to the oil cooler, and a small low pressure return line from the power steering valve. That small line returned at the point marked PB, where it used to dump the power steering valve's return to tank oil into the low pressure cavity on the travel control valve, kind of using the travel control valve as a T. From there, the return to tank oil makes its way first through the oil cooler, then through the oil filter, and finally back into the tank. In this new design, there will still be 3 lines attached to the travel control valve. It will still have the high pressure feed line coming from the pump. It'll have a new low pressure line leaving from the standard return to tank port. And it'll have a new high pressure feed line leaving the new power beyond port. That new line will head outboard underneath the right side footrest. At rest position, the high pressure oil entering the travel control valve will all pass through and exit via the new power beyond port, where it will make its way underneath the right hand footrest and ultimately arrive at a quick disconnect in front of the right hand footrest. If you activate the travel spool, the high pressure oil will head from the travel control valve through the travel motor and back, causing the tractor to move. After passing through the motor, that same oil will make its way into the lift circuit gallery, where it's available for use by the lift cylinder if needed. From that galley, the oil is directed out the power beyond port. So whether the tractor is in motion or not, there is always flow out of the power beyond port, straight into the quick disconnect in front of the right hand footrest. Using the loader while the tractor is in motion will cause that pressure to get split between the loader function and the travel function. So the tractor may slow down a little bit while the bucket raises or whatever, but neither function ever gets completely starved of flow. With the lift spool activated, the oil will head out one of the lift ports through the lift cylinder and back into the other lift port, and then get dumped into the new return to tank line. So the new return to tank line can be much smaller than before, because all it has to handle is oil coming from the lift cylinder, and only when the cylinder is actually moving. Most of the time, there will be no flow in that line at all. So we now have two small lines and one large line that all need to be connected to the tank. The original small return line from the power steering valve, the new small return line from the travel control valve, and a large line that'll be coming from the quick disconnect out in front of the right-hand footrest. To accommodate all that, I've changed the return oil flow a little bit. I've used standard half-inch NPT pipe fittings and created a multi-port return-to-oil manifold just forward of the oil filter in the right-hand side of the tower. All return oil will be routed into that manifold. From there, it'll pass through the oil filter and then through the oil cooler and then up into the fitting on the bottom side of the tank. The return-to-tank manifold consists of a regular half-inch NPT T that'll be connected to the new return side quick disconnect and a small pipe nipple onto which I've welded two JIC6 male stubs. Half-inch NPT fittings are rated for about 300 psi, which is plenty strong enough for this location in the system. The only thing hindering the flow from this point on into the tank is the oil filter and the winding shape of the oil cooler. So this location will never see more than about 50 psi under any circumstances. Note that you would never use standard NPT fittings anywhere on the high pressure stream, as they're going to blow out immediately. The two smaller return lines from the power steering valve and from the travel control valve will screw into the JIC6 stubs that I welded on, and the half-inch line with the quick disconnect will just stick out of the right side of the tower. The tower access cover will be modified to allow for that pipe to stick out through there, and I'll add on a bracket to strengthen that line. So now there will be two quick disconnects in the vicinity of the right side footrest. A lower outer one that'll be 2000 psi high pressure, and an upper inner one that will be the low pressure return. With the loader attached, you'll just hook up two hoses to the new loader valve, one to supply it and one to return from it. With the loader detached, one of those hoses will hook directly from the pressure supply into the return to tank fitting. The high pressure flow has to always have a path to make its way back to the tank. So there must always be a connection from the pressure fitting to the return fitting. The flow can either route into and through the new loader valve, or the flow can be directly connected by a single hose. Now, if you were to try to start the machine without that connection hose, that loopback hose connected, then all of the pressure side fluid will have no normal path to make its way back to tank. In that case, the travel control valve's pressure relief valve would have to pop open at around 2100 psi, which would allow the oil to flow back to the tank via the travel control valve's return hose. But because the pump will be facing 2100 psi back pressure, it seems like it'll be pretty hard to get the tractor to start in that condition. If the loopback hose were to come off while the tractor's running, then the relief valve would again trip. But there's no real risk of damage or injury in either case. For the high pressure supply side, I'll come out of the travel control valve with a short hose that'll just provide some vibration damping and make it easy to get the line to turn and twist down and out of that tight space up in there by the frame rail. From there, I'll run standard steel half-inch NPT pipe joined with special purpose 4000 psi rated carbon steel pipe fittings. I want to take a minute to note that I am not using standard iron pipe fittings for high pressure hydraulics. There is a dramatic difference between standard steel pipe and standard iron fittings. The pipe is rated at about 5000 psi, but the fittings are only rated for 300. Standard black iron NPT fittings cannot ever be used for pressure side hydraulics. They will absolutely fail, and probably explosively, causing damage to equipment or injury to people. The steel pipe will be routed out under the footrest, but above the loader crossmember. The relatively heavy steel pipe has enough inherent physical strength to support the free-floating quick disconnect without having an additional support bracket. But on the return side, I will manufacture a support bracket that will be bolted onto the tower and clamp onto and stabilize the return side pipe. It took several days to fabricate and install all of this, but at the end of several months of starts and stops and dead ends, It looked like the end was finally in sight. I should have known better. After going through a mental checklist that I had all the various lines connected, that all the joints and fittings were tight, I filled up the reservoir with 6 quarts of fresh oil and started it up. To my pleasant surprise, there were no gushing leaks, and the tractor drove as normal. Things can't be that bad, right? But I needed confirmation that I can in fact operate the loader valve while I'm driving. So I connected the new loader valve into the pressure stream, installed loopback hoses on the work ports, and took a drive, and then tentatively pulled the loader handle while slowly driving. And success! I could now hear flow going through the loopback hose, and I was rolling along at the same time. But remember, once I've reinstalled all these parts and the structure of the loader frame back on the tractor, the hydraulic components down underneath become very difficult to access. So I need to be sure this is right before I continue. So one last test before I go on. What happens when the loader valve is dead-headed? You see, when the handle is pulled back and the cylinder reaches its end of travel, then that line is basically a dead end, and the pressure relief valve has to kick in. You'll hear the engine audibly bear down under the strain, and you can hear the pressure relief valve whining as it releases the excess pressure. I decided to simulate that event and observe it all working as it should. So instead of a loopback hose, this time I installed a plug in the valve's work port. Then when I pull the handle, the loader valve is dead-headed, and I'll listen for the engine to bear down and the relief valve to kick in. So I started the engine, throttled it up, and gingerly pulled the handle. And nothing. No engine change, no whining relief valve. So I throttled it down and tried it again. I thought maybe at idle I could hear just a little change in the engine RPM, but hardly at all. And I couldn't explain that. If I have high pressure leading to this hose and I block off that hose, then that pressure has to build up, right? The back pressure should at least bog the engine down a little bit, right? Well, let's do a pressure test. So I grabbed the 12,000 psi gauge off my hydraulic press and cobbled it onto the end of a hose and connected that hose to the work port. And I repeated the engine running pull the handle test, and the gauge did move all the way up to 400 psi. And that was the ugly surprise, though if I were smart, I should have anticipated it. Remember how the flow works going through the travel control valve. Oil enters the travel motor galley, then dumps from that galley into the lift circuit galley, and then goes from that galley out the power beyond port. Now the tractor travel control valve has 2 different pressure relief valves, one for each of those galleys. The motor galley relief trips at 2100 psi, and the lift circuit relief is set around 400 psi. The deck lift cylinder is fairly light duty and doesn't need to be that strong, so 400 psi is more than plenty for that little cylinder. If you do overpower it, you're going to blow out the cylinder because it's just not made heavy enough to withstand 2000 psi. So the realization hit me that since the power beyond is downstream of the lift circuit, the power beyond has the same effective pressure that the lift circuit does. That's why the engine didn't strain, and that's why the pressure gauge only went up to 400 psi. Now when Case built their loader, they simply dialed up the pressure in the lift circuit to about 12 or 1400 psi. The deck lift cylinder can deal with 1200 psi, and then they designed the loader to operate on that relatively low pressure. The way they got around the lower than normal pressure is they used lift cylinders that have a larger than normal diameter. So the greater surface area of the piston inside the oversized lifting cylinders allows you to use that lower pressure and still achieve the same force that you need. But in my case, I used standard size lift cylinders. When I have 1,000 pounds in the bucket and try to curl it backwards, I'm going to need an absolute minimum of 2,000 psi to act against all that weight and torque. And I cannot just crank up the pressure relief on the lift circuit. If I do that, I'll have to replace the lift cylinder and repipe the entire lift system, both for the deck and for the 3-point hitch. So I find myself with plenty of flow, but now lacking in pressure. So it's decision time yet again. Either I tear everything back out, plug up the new hole that I've just put into the travel control valve, and go down the road of the flow divider, or I find a way to dial up the pressure in my lift circuit without destroying all the components that are currently in my lift circuit. Now, needless to say, I'd far rather make this work, since it's all but installed, and it's the very best case where flow is concerned. So I mulled it over for a couple days, imagining how I could replace or reinforce the deck lift cylinder, what it would take to replace all the lift lines and the diverter valve with heavier duty versions. But wait, what if I could introduce a pressure relief tee into the lift lines themselves after the oil has left the valve body? Then I could crank up the lift circuit's pressure relief, but that higher pressure would vent harmlessly before it ever reached the various lift circuit components. However, I would have to have two different relief valves, one for each work port. The raise-up line's relief valve wouldn't do anything to help the lower down line, so each line is going to need its own separate valve, and they cost about $100 each, and it's going to be a rat's nest of hydraulic lines to hook them both up. So, does anybody sell a dual port relief valve? Not a single relief valve with two ports, because we can't let our two lines intermingle. If the fluid from the raise-up side can bleed into the lower down side, then the fluid will always just bypass the cylinder and leave the cylinder inert. So the dual ports have to be isolated from one another. Does anybody sell a dual isolated port relief valve? Not that I can find. But it shouldn't be that hard to build one. You'd need to create the proper chamber for the relief ball and spring to ride in, with a screw to adjust the spring pressure. You need to create two inlet ports that both have a path to reach the pressure relief ball, and each with a ball-bearing check valve to ensure that the two ports are isolated from one another. That fluid entering one port cannot backfeed out the other port. At this point, I felt like I had little to lose by giving it a try. If I could successfully build and install this final component, then I've made it over the finish line and I have a working loader valve. If it doesn't work, then I have to tear out everything I've done and go down the flow divider path. I had a 4-inch by 6-inch block of 1-inch thick plate, and I drew up plans for a dual isolated port pressure relief valve based on those dimensions. As I worked on its design, it occurred to me that it was going to be a challenge to direct the output of this new pressure relief device into my return to tank manifold. It looked like I would have to remove my newly installed manifold and add a new port into it. But adding a new hose fitting into that tight space was going to be tough. Then I realized I could integrate a T function into my new device. I could just create a T cavity in its output section, and then this device can dump its return fluid into the manifold at one of the ports that already exist. And I can direct the power steering valve's return, moving it from the current manifold into this device. So my plans were finalized for creating a dual isolated port pressure relief valve with integrated outflow T. I removed the pressure relief ball and spring from my existing treble control valve and replaced them with a slug insert that would completely block that port, so it no longer functions as pressure relief at all. In the process, I measured the size and depth of the spring chamber so that I could machine an identical port into my new component. I machined that port and the other parts of my newly invented hydraulic device. I didn't have the right springs for the inlet check valves, so I wound a pair of springs on the lathe using some spring wire. After I assembled the new component, I tested it with 100 psi air pressure. I ended up having to lap the seat where the pressure relief ball seals. After lapping that seat, I had satisfactory seals against air pressure, and if it'll work for air, it'll be fine for heavy oil. Installing the new component into the tractor was a struggle. I had to add these very tightly bent and twisted 3/8 steel hardlines into an already cramped space. After a few more hours of struggle and frustration, it looked like everything was installed and everything was tight. Time for a leak, function, and pressure test. First of all, there were no leaks. That's good news. Secondly, the tractor does drive, and both the deck and the PTO lift do go up and down. Then I installed the loader valve and rigged up the pressure gauge again. and with the engine running, I gingerly pulled the valve handle to send the pressure to the gauge. And it was very gratifying to hear the engine bog down, hear the loader valve's pressure relief valve start tripping, and see the pressure gauge rise up to read 2,300 psi. That means that I finally have full flow, high pressure oil to my loader valve. The minor step of piping in a new valve has taken 9 months and repeated iterations of work, frustration, and redesign. But it's finally over. The only thing standing between me and a working loader is the simple task of mounting the loader valve in its place and piping in the lines from the valve to the cylinders. And finally, one sweet morning, I had for the first time working hydraulics to my loader. And everything worked honestly better than my expectations. In that video, the tractor is simply idling, but the hydraulics are responsive and plenty powerful. Now, if you made it this far, I don't know whether to wish you congratulations or my condolences. But I hope you've enjoyed the journey. This particular segment of the journey was not a fun one for me, but I do feel a great sense of accomplishment now that it's behind me. As it says in the title, this is the Phase 5 story. I've released a companion video alongside it, the Phase 5 result. So if you want a close-up overview of how everything actually turned out with the hydraulics, please check out that video. We're in the home stretch now, 1 or 2 more videos to wrap everything up. And as always, thanks for watching.